Hi, this is Dave Johnson. In the previous video, we talked about the best way to measure the light that plants use for the photosynthetic process. Now, this light energy has wavelengths that fall between 400 nanometers and about 700 nanometers. And this waveband of light energy is called the photosynthetically active radiation, or PAR. And in that video, we also talked about using a PAR sensor to accurately measure the intensity of light in that PAR waveband. So that light energy in the PAR waveband, whether it comes from the sun or artificial lights like these, often looks white, but in reality, it's a lot of different colors. And what we typically do when talking about plants and light is break it down into three distinct wavebands: a blue, green, and red. Now, while we have a PAR sensor that can accurately measure the intensity of PAR, whether it's from the sun or these artificial lights, what this sensor can't do, for example, is tell us if this particular light has a slightly higher intensity in the blue wavelengths or in the red wavelengths. So why is it important to know the light quality or the spectral output from either the sun or these artificial lights? Now, there's a lot of research out there showing that various wavelengths can have various effects on plant growth. Everything from the photosynthetic process to the morphology of the plant. Furthermore, there's research supporting the effects of light outside that 400 to 700 PAR waveband. For example, UV and far red. So growers are now applying various colors at various times over various intensities, and all of these can have significant effects on yield, stimulation or inhibition of flowering, the shaping of plants, whether they're tall and thin or short and bushy, the chemical content, for example, of cannabis, or how vegetables look, the color, the taste. And there's even wavelengths of energy that help protect plants from bleaching or from insects. And there's even new research that shows how some wavelengths can even promote pollination. So in this particular video, we're going to spend some time talking about this device. It can be used to measure the light quality or the spectral output from various light sources like the sun or artificial lights. For a quick sneak peek, I'm going to go ahead and take some measurements of these two different light sources behind me. So here is the first one. And here is the second one, and you can see it's significantly different. So let's go back inside and talk some more about this instrument.
So as a quick recap from that first video, we had a discussion on the difference between radiation and light. We looked at the electromagnetic spectrum, where we have shorter, higher energy waves at one end, longer, lower energy waves at the other end. But what we're most interested in is this section here of the spectrum, where we have light and energy that comes from the sun. Now, also in this area, we have a small band of radiation waves that the human eye can see, or the visible light. Now, the length of these waves are several hundreds of nanometers. And the key concept here is that each color has a different wavelength. For example, red is about 700 nanometers long, while blue light is at around 400 nanometers. So also in that first video, we talked about how the human eye sees light versus how plants see light. We took a cellular level look inside a leaf at the chloroplast, where that light energy comes in and has photochemical reactions with protein pigments inside the chloroplasts. Now, there's a variety of pigments in there that have different functions. In addition, each pigment best absorbs specific wavelengths of light, or in other words, is more efficient. So in that first video, we primarily focused on the 5 photosynthetic pigments that absorb and utilize the light energy that exists between the wavelengths of 400 and 700 nanometers. Also known as the photosynthetic active radiation, or the PAR waveband. Now, in actuality, there are about 10 to 15 primary leaf pigments that can be broken down into 3 groups: photosynthetic activity, photomorphogenesis, and then photosynthesis in algae. Now, let's imagine that we can apply lights with specific wavelengths to those pigments where they have their peaks or where they're most efficient in their absorption, and we could change how the plant behaves. For example, could we maximize our photosynthesis? Could we help prevent disease? Could we stimulate or inhibit flowering, change chemical composition, and even change colors and taste? Now, knowing this information, we can create what can be called light recipes for the vegetation we're growing. For example, when to apply lighting, what type of lighting, which wavelengths, the duration of that lighting. Now, different plants require specific light schemes throughout their life cycle, and with the new lighting technologies out there, we can optimize the lighting strategy for the desired results we want. So take a look at the spectral outputs from two different light sources here. The top one's an incandescent bulb, the bottom one a fluorescent. Now both of these are considered white light, but you can see the spectral quality is quite different between the two, and plants would grow differently under each of these. So let's consider the example where we have this particular LED in our grow room, and we want to know what the spectral output and quality is. How do we go about measuring this? So there's an instrument called a spectrometer, which actually splits the light into an array of separate colors called a spectrum. And some of these devices can then measure the intensity of light at each of these wavelengths. So when making measurements of light with respect to plants, there's three key variables we want to understand. The photosynthetic active radiation, or PAR, which we discussed in the first video, is the band of wavelengths that fall between 400 and 700 nanometers that are primarily responsible for the photosynthetic process. Then we have photosynthetic photon flux density, or PPFD. Now this is the actual value or the number of photons, or what can be considered the intensity of the energy that's falling in that PAR waveband per unit time per unit surface area. Then we have the photon flux density, or PFD. This is similar to the above variable, but not only does it include the PAR waveband, it also includes the energy outside it, for example, in the UV and far red ranges. So in that first video, we talked about the benefits of having a good PAR sensor for measuring light intensity. Now let's discuss the differences between the PAR sensor and a spectrometer. Now both instruments can measure light intensity within that PAR waveband very accurately, regardless of what the light source is. The main difference is the spectrometer can also measure down into the UV range, as well as up into the far red range. Now with the PAR sensor, there's no real indication of spectral quality, only the quantity. So for example, if we measure the intensity, we're not going to be sure if it's from shorter blue wavelengths or longer red wavelengths. Let's now take a more detailed look at a spectrometer.
Okay, in just a minute we're going to go outside and make some spectral measurements of the sun. And then we'll go over into the greenhouse and make some spectral measurements of the artificial lights that are used inside the greenhouses. But let's talk about the instrument we're going to do that with. This is a Li180 spectrometer. What we'll do is sort of an unboxing. So if we open it up, we have this canvas protective carrying case. Inside here is the actual spectrometer. You can see here we have a touch screen. Under the protective cap is the sensor. We'll talk a little bit more detail about that in a minute. We have our power supply, the cable, and along with that there's 4 or 5 different plates here with different fittings, so you can mount this in international countries and charge the batteries. This is a tripod mounting bracket, so if we want to make measurements with the spectrometer, we place that in here and set it up to make continuous measurements over time. This is mounted on a tripod and it can keep it stable throughout the process. We have a USB cable for connecting the device to a computer to download the data and the files, where there's some really nice analysis software to take a better look at the data. This here is an extension cable, so there might be an instance where you want to make a measurement that's further away from where you're able to get, maybe up on a higher shelf. This allows you to make that measurement and still look at the console in real time to see the data and the results. Now the Li180 comes with an SD card installed, but this is another one that comes along with it. This one actually comes with a Wi-Fi chip, and this Wi-Fi chip gets inserted into this SD card, and then they both can be inserted into the Li180 spectrometer, so you can connect and use your spectrometer with a mobile device. Finally, we have a little illustrative manual here that allows you to get the instrument set up so you can get going and making measurements. So let's talk a little bit more detail about some of these components. So here we have a touch screen which allows us to navigate through the different menus, take measurements. Here we have a rubberized protective calibration cap that covers a CMOS linear imaging sensor. And the optics here allow us to make measurements of light intensity in 1 nanometer increments. On the side panel here we have the capture button, which allows us to take the measurements. There's also available one on the touch screen. On this flip side here, you can see we have a power port. That allows us to charge a lithium-ion battery that's in here that allows us to give over 5 hours of portable measurements. We have a USB port for connecting to a computer and transferring data and files back and forth. Here we have the power button, and here is the SD port. Now I talked about that combination card.
This part here is the Wi-Fi card, and we have an 8 GB SD card that simply slides in there. And the combination of these cards, when inserted inside the device, can be configured so that this can be controlled by a mobile application, for example, an iPhone or an Android. Now, the other thing I talked about earlier is that you can take apart the console and the head, and let's say we want to make measurements off at a distance. Then we use this extension cable and we can insert that into the port here. The other end connects to the head. And what we can then do is make measurements and control the device and see the data coming in real time, even though the sensor head is located in a different location. And we can just put the two of those two back together as such. Now let's go ahead and power on the instrument. And every time we turn on the instrument, we're going to be prompted to do a calibration. So this is really easy to do. It's called a dart calibration. And we hit OK. And what it's asking us to do then is to place a rubber cap over the top here. That keeps any light from getting down into the sensor. We simply hit OK. This usually only takes about 5 seconds to complete. Now we want to do a calibration basically every time we start up the instrument. We also want to do a calibration if we're moving from an area of high light intensity to low light intensity and vice versa. And similarly, if we ever move between, say, an environment of high temperatures to low temperatures and back and forth, you'll want to do a calibration at that point. So basically that's it. We're ready to go outside now and make some measurements in the sun.
All right, I'm going to do a demonstration here to show how quick and easy we can get spectral measurements with this device here. So the first one we're going to do is indirect sunlight. I'm going to put this parallel with the ground, sun's off at an angle, hit the button. Right away, results are on the screen. Let's take a look. And we can also do some other similar measurements, for example, direct sunlight. Aim this at the sun, push the button. Now while the intensity is going to be higher, the spectral shape should be the same. However, let's do a diffuse measurement now, where I'm going to shade the sensor with my body, take a measurement. Now we expect the intensity to be lower, but in diffuse light, we also have a different spectral output. Let's take another look. So let's go inside and take a closer look at the measurements we just made, and also talk about some of the other software tools inside the instrument.
So with the Li180 spectrometer and its software, we can generate spectral output plots from the measurements we just made. So for example, this is the direct sunlight, the second one is from the indirect sunlight, and this third one is from the diffuse sunlight. And you'll notice that this third one has a slightly different spectral quality than the other two. Now the direct and the indirect sunlight have similar spectral qualities, but if you look at the light intensity there, you can see that's where the difference lies. Now let's take a closer look at the intensity from these measurements. And we have a plot here of the ppfd on the y-axis, wavelengths across the bottom, and our three measurements. Now let's highlight the area where we have the photosynthetic active radiation. And if we want to know the intensity in that PAR waveband, we integrate under the curve. So for example, we do this for the direct measurements, and we can do the similar for the indirect and diffuse measurements and have light intensity measurements for each of these. And we have some additional spectral information here. In these yellow boxes, you can see that the light intensity, or the PFD, has been broken down into the blue, green, and red wavebands. And if I was to summarize these three values up, I'd have the same intensity for the entire PAR waveband. And when I talk about the blue waveband, we're talking about all the light energy that has wavelengths that fall between 400 and 500 nanometers. Similarly, for the green waveband, it's light energy with wavelengths between 500 and 600. And for the red waveband, we're talking about light energy that has wavelengths between 600 and 700 nanometers. So some questions may arise on how accurately the spectrometer measures the intensity of light within that PAR waveband. So we can do some comparisons to the Li190R PAR sensor, which is the industry standard throughout the scientific community. It's been in use for 50 years now. And here we have a plot of the one-to-one relationship, and we can see that that looks really good for these sunlight measurements. Later we'll add in points from artificial light sources and see that that same relationship holds true. So let's circle back to the spectral plots from our outdoor measurements and talk about the PFD values that fall outside of our PAR waveband. So over here we have the UV waveband, which has light energy with wavelengths between 300 and 400 nanometers. And over here we have the far red waveband, which has light energy between 700 and 800 nanometers. Now if we look at the actual data, we can see that the PAR intensity is going to be a little bit less than the intensity over the total measurement. And again, that's because the sunlight does have that light energy in both the UV and far red ranges. Now if we want to see this in even more detail, we can see the light intensity in both the UV and far red wavebands for each of these measurements. And that can give us some interesting information, for example, how that ratio drastically changes in the diffuse sunlight. So let's go ahead and look at more detail and some of the cool features and measurements we can do with the Li180 spectrometer. Okay, this is the home screen once you power up the Li180. And we're just going to take a look and do a quick tour through some of the main functions that you'll be using mostly. So to rotate between the two home screens, we simply use this arrow key, and you can go back and forth between the two screens. One of the main functions here we'll use is PPFD. Again, that's photosynthetic photon flux density. So in here you have the total intensity between 400 and 700, and then you can see it's broken down for intensity for the blue, green, and red color wavebands. And whenever we want to go back, we just push this home key, and that brings us back. So one of the other functions we'll use a lot here is the spectrum. This is actually a plot. And as you can see, when you make a measurement, it has a nice colorful chart here showing the relative light intensity at each of the wavelengths. And some of the other functions we'll cover in yet a second video are custom wavebands. So if we go in here, we can actually set up and look at the intensity at wavebands that we feel are most important. Similarly, we have a ratios buttons where we can customize the ratios between different wavebands that we're interested in as well. So we'll cover those in a follow-up video. PFD, so that's photon flux density. So again, this goes outside the PAR waveband. It goes down to 380 and up to 780. And so besides the PAR waveband, you can also get the PFD for the UV range and the PFD for the far red range, and get that intensity along with the red, green, and blue, and you can click on the menu to pull up one of those variables as well. So go back to the home screen again, and now let's take a look at the second page. So here we have the logging functionality, and I'll talk about this in a little more detail in a bit, but that's where we set up our continuous logging. Here is an important screen. This is variables that we're interested in. So anytime you go there to access it, you're going to be shown 4 variables, but you can click on any of these and you can see there's a very long list of about 50 different variables. And so you can decide to pick which ones you want to show on your display here. For example, we show a ratio and some of the other PPFD values as well. And we'll go back to the home screen. Here we have options. I'll talk a little bit more about those in just a moment. And then we have a grid tool, which I'll talk about in a follow-up video, and how this is useful to be used to make repeat measurements in and around a greenhouse, for example. And finally, we have this browser, and this allows us to look at past images and data files that we've collected. So that's a quick summary of some of the most used tools in the 180 software. Okay, let's consider the situation where someone is trying to shorten the number of days to flowering. They'd be interested in the light source and the ratio of red to far red light coming from that. Perhaps they're even interested in inhibiting flowering. So they'll want to know the amount of blue light coming from their light source. Maybe there's even someone that wants to know how to improve the color of the lettuce or their kale. They're going to look at the red to blue ratio in that instance. So the new feature installed in the software here are those ratios provided in default. If you go to the variable tool here and select on one of these variables, what you'll notice amongst those variables are 9 ratios that are automatically delivered each time you make a measurement. So 6 of these are just 2 wavebands, for example, red, blue, red, far red, etc. and that ratio is computed every measurement. You'll also notice that we have two ratios, which are three wavebands. For example, blue, green, red, blue, red, far red. Now, while you can't compute a ratio when you have three variable wavebands, what the instrument will do is break down the light into the fraction of light from each of those wavebands. And you'll notice we also have one over here, one final ratio, which actually breaks the light down into all 5 wavebands, so you know the percentage of light coming from each of those. So those can be very useful for trying to grow your plants and control what's happening inside your greenhouse or growth chamber.
Okay, let's talk about if we want to set up the spectrometer to make automated logged measurements. So we can find that function by going to the second page on the home screen, and you can see we have this logging icon here, and we have some variables, but let's first go into the settings menu by clicking on the gear here. And we have some options. So this first option is the integration mode. So we have two options of either setting that to manual or automated. So the integration mode is how many milliseconds you want to have the measurement taken for. So you can set it for 200 milliseconds, 2000 milliseconds, and you do that through the manual mode. Or otherwise you can use automated mode, and that integration time will be changing based on what the light intensity is. So we'll go ahead and leave that on automatic. Here is where you would set that integration time if you did it in manual mode, so we're not going to do anything now. This just turns on the beeping for when you have measurements being made. And then this last option here is called the log mode. So if I click on count, what I will do is then enter the number of measurements I want to make, say 10 measurements, 100 measurements, 1,000, and then I pick an interval time that I want between those measurements. And when I hit start, it'll simply go through the number of measurements that I selected to be made. So the other alternative here is to pick time mode. And when I do that and come back out to that logging screen, here's where I have my integration time. It's currently set to 2000, but again, that's going to change because we're set to automated mode once the measurements begin. And then here we can select an interval where we want to make measurements, for example, every 10 seconds or every minute, every hour. We can set that up to do so. And then down here, we pick the start time and the end time for the measurements. So the way this is currently configured is we're going to make measurements for 1 minute, and we're going to do it every 10 seconds. So we'll collect 6 data points and log those points as well. And when we're ready, we simply hit this start key. Now, it's going to be waiting until this time gets reached and then start conducting the measurements. Now, this will happen every day, so we don't have to go in every day and reset this up. It'll just make measurements at the exact same time the following day. Now, something we want to keep in mind is that we want to connect the device to AC power. You can see even here on our device, we have a low battery indicator. And so if we're going to be making continuous measurements over several days, several hours, we'll probably want to connect the device to AC power so we can make sure all our measurements are collected.
Okay, now if you've used that logging feature, the output that's generated is stored on the Li180 on the SD card on a folder called log. And if you access that log folder, you'll see those files that you set up and logged with the instrument saved in a .txt file. That allows you to open it in Excel or WordPad, something like that. Alternatively, if you want to do further analysis on that data, you can bring those into the new Li180 Windows software. Now, let's talk about the types of files that are output from the Li180. You have what we call the ESPD file, and you have a micromole file. And you also have an image file, which is stored in this folder up here. But the difference between these two files, I have them open here, is here is the micromole file. And basically the only thing in this file is the PFD measurement in micromoles per meter squared per second at each wavelength. Okay, that's all that's in that file. Over here you have a more informative file in the ESPD file shown at the top. And in this one, you can see there's some header information, but then there's also information on the intensity levels at the various wavebands, both the default ones and custom ones. There's a lot of information here on the different ratios of light in each of those wavebands and custom wavebands. Here are those standard default ratios we talked about, custom ratios, and so forth. And eventually you get down to the wavelengths and the measurement. Actually, this value is in milliwatts per meter squared, but when it's brought into the Windows software, it's converted into micromoles per meter squared per second. So those are the two file types that are output with each measurement. If we look at a picture here, I have one also open for that same measurement, and you can see it basically gives you a snapshot of the measurements that were made in those different wavebands, and also an image here of the spectrum of what that light output was. Okay, so now we're going to take a look at the new Li180 Windows software. This is version 1.5. Now there's primarily two different ways to look at data from your Li180 spectrometer. One of them is to put the Li180 in mass storage mode, transfer files from the unit onto your desktop or PC or onto an external hard drive, and you can bring those into the software and analyze them that way. Alternatively, you can set the device up to do a PC connection, and if you do that with the USB cable, you'll see the device show up here as available to connect to. Now, something else to point out here is if you want to use the Windows software with a different language besides English, you can go ahead and select that from the choices there. So for this demonstration, I'm going to use data that I've already transferred onto my PC. So I'm going into this view mode. Now from here, I'm going to load data. I have a couple options. The first one is for files that I've already transferred to my PC. This multi-record is for if I'm using the Li180 as a connected device. So I'm going to choose this first option. And once I go in here, I can access all the files I've collected from my 180. I'm going to go ahead and select one of these files and open that up. What you'll notice here is the spectrum, a plot of the spectrum over the wavelengths across the bottom. This first data you see is normalized. Okay. Down here you'll see a table with a lot of the information, the model number, serial number, measurement time, file name, that sort of information. If I scroll all the way to the right, what eventually we'll see are some of the useful information, for example, where the peak wavelength occurred. Here it's showing 631. Alternatively, I can come up to this toggle switch and it will put a nice red line there where that peak is, so I can see it. Other information here is our PAR measurements for this particular light source. Here it's PPF and PPFD. Then we also have a breakdown of the intensity for each of these wavebands from UV, blue, green, red, and far red. And then we also get a photon flux density measurement for the entire range from 380 to 780. A couple ratios are computed here, blue to green and red to far red. Those are just there by default. And over here we have a small table as well showing some of those results for this measurement. If I want to look at some other variables, I click on this icon here and I can move variables in and out of the list as I want to take a look at those. Okay, let's now take a look over here at the different modes. We have the view mode, which we came into, but the other one that's could be quite commonly used is this log mode. So if I click on here, this is where I've taken measurements, say over a time frame, say once every 10 seconds for the period of a day or an hour, something like that. Again, I'll just bring in a data set I've already transferred to my PC. As we talked about earlier, we have a log folder that's automatically created. And inside there, if I've done any log measurements, I can go ahead and select one of those, open it, and bring that into the file. And here now you can see each of the different wave bands and what the intensity was at each of these 6 measurements that I made. If I want to see in more detail, I can just display the units on here, and that allows me to see what the intensity was in a quick snapshot. Okay, now if I am connected to the instrument, I can also do my logging from here with the start logging and stop logging. and collect measurements as long as the Li-180 is connected.
So that wraps up our introduction to the spectrometer, where we saw that we can use that device to measure the spectral output from the sun, spectral output from artificial lights, or from both. Now in our next video, we're going to take a look at some more advanced features and tools in the instrument. For example, let's imagine we're interested in the intensity and specific wavelengths. We can customize our own wavebands. We can also customize ratios of different wavebands to see where the intensity of light is falling more. And then a really awesome tool, what we can do is look at the spectral output from the lights, see where those peaks are, and see if they match up at all with where those protein pigments have their best absorption of light for photosynthetic processes or other growth characteristics. Now another tool we'll look at is the grid tool. That allows us to rapidly walk through a greenhouse making instantaneous measurements and also get an average value over the whole area. There's also a transmission tool we'll look at that allows us to see how much light is penetrating through the glass. Not just the intensity, but the light quality, so we can see if there's any change as that light comes through the glass. Finally, what we'll do is we'll take that spectrometer, we'll go measure some artificial lights inside the greenhouse, and take a close look at that spectral output. So we invite you to come back for that next video.